Did you want to go first, Rob?
Sure, I'll just welcome everyone here to our first Mentoring Monday of June. And this is supposed to be our kind of open forum. So if you've got questions that you're trying to figure out how to approach, this is the particular Mentoring Monday of the month that we can focus on those. If you email them to us ahead of time, that makes it work better. So I don't look like a total clown up here, not remembering how to apply a formula to your problems that you're coming up with. And if you're going to be taking one of these exams, I want to just share an email I got yesterday. And I'm not sure why my former colleague Mark emailed me this, but he said, wanted to thank you for the support, education, and advice. I think the biggest factor, at least for me, was buckling down for a few months to study and practice. Just like you advised me on the first day, I questioned you regarding best practices on taking the exam. So Mark had passed his exam, but this email just kind of popped up. So yeah, buckling down and studying is definitely the key, and hopefully we can help you with unraveling some of the mysteries of the survey universe. I think one of the keys is have a calculator that you are very, very comfortable in using. I prefer the HP series because I've been using HPs since before most of you except George were born. So I'm a fan of the HP 33S and 35S, and if you can score those online somewhere, that's good. If you don't like those, just make sure that whatever calculator you pick is on the approved calculators list, because it would be probably pretty disheartening to be partway into the exam and have somebody say, hey, that's not on the approved list, so your exam is forfeited. So that's about it. Are there any questions? Let me grab a pen. Are there any questions that anybody is really chomping at the bit to learn before I turn things over to Dane? And then if there's something that is giving somebody trouble, I'll write it down and I'll look up the how to do it while Dane's telling you about horizontal curves. So does anyone have anything? All right. Well, with that, yep. Somebody, Sean? What do you got, Sean?
Okay.
Not hearing you, Sean. Still not hearing you, buddy.
Okay, you can probably hear me now, right?
Hey, there we go.
There we go.
Okay, great. So I'm scheduled to take my FS exam in October. And one of the items that I was hoping to get some, kind of clarity on is photogrammetry, some takeaway points on what's important, definitions of, common things that are, discussed in photogrammetry. I've laid out points and stuff like that, but I've not actually done the processing end of things in the office and, submitting a completed project and the planning and stuff. So maybe a little bit on that without getting too crazy.
Okay, for anyone, just photogrammetry in general, if you can visualize the triangles that you're dealing with in photogrammetry, that makes a whole big difference. The triangle from the focal point of the airplane down to the ground, and then the focal point of the camera to the actual exposure surface itself. So if you're typically using a 9x9 film camera, you've got that focal point in the lens, and then above that would be that film camera. But to make it easier to visualize, just flip that down so that at the top of the big triangle that represents the focal point down to the ground is the focal point down to that film camera. Let me find you some resources while Dane's talking about horizontal curves. And again, on any of these exams, go to the exam plan and look and see which items are photogrammetry for you on this case, and then look at the contents of the exam materials to see what kinds of formulas and definitions and things they give you there. All right. We got one chat bouncing in, and confused on the words. Polaris observations and how to plug them into the formula. I don't know that any astro is going to be covered anymore, because
I've heard the same thing. It's going to be very limited, if so.
Rather than worrying about astronomics, which I think George and I probably had to deal with, maybe Jerry had to deal with back in his early career. Other than that, probably not something that's going to be covered. Check the exam plan. And if somebody wants to look at at some materials on that, might be something to help you if you're suffering from insomnia. Other than that, it's probably not useful.
I brought it up when I missed my last test last year and failed. I had 3 questions on Polaris observations on my NCS test, so that's why I brought it
On
up.
the fundamentals, seriously?
Yeah, on the FS.
Really? That's pretty.
Were they
surprising.
more definitions based, or were they actually expecting you to?
I think there was 1 or 2 definitions, at least on my particular test, and there was one where I actually had to go through the entire formula.
Huh. All right. I'll look up something
I've
on that
changed
as well.
since then,
Yeah.
but
Hey, Rob, if you wanna focus on the Polaris stuff, I got some good stuff on photogrammetry.
Yeah, I think I got some resources that I can post up for both of these.
All right.
This is Jerry Mahone. I've got some material for photogrammetry also from a review workshop that I did a number of years ago. I can contribute that also. That goes back to the geometry that Rob was talking about with visualizing the triangles and the exposure point and the terrain and scale equations and all that.
All right.
Well,
I'm sorry, go ahead.
if you guys are concerned about definitions of different things on the test, ASCEE has a great book of definitions and terms for surveyors and engineers. That's the only book I took into the exam. That and the BLM manual, which was probably useless, but that's a good source for definitions. I mean, if you go through that and get some variable terms in there, you're good to go.
All right. With that, I'll turn it over to Dane for some horizontal curve stuff.
Yeah, and then I'll go into photogrammetry. My entire manual and what I think your focus should be whenever you're taking this test or studying for the test. Well, first let me start there. I recommend about a half hour to an hour a night for about 4 months is about what I would recommend. And you can give yourself off Saturday, Sundays like I did. But I would say a good 5 hours a week, good solid 5 hours a week. And what I did was I found that 1001 Fundamental Survey Questions book by Jan Van Sickle. And I went through about 20 to 30 problems a night in that book. And that book is amazing. It does two things for you. First off, it puts you in a mindset of taking a test, because the whole book is geared in a question with multiple choice answers. So you're going to get yourself in that routine of seeing questions and trying to eliminate the stupid answers, keeping the relevant answers, and trying to narrow it down. So it gets you in that test-taking mind frame. And then secondly, it covers absolutely everything: legal aspects, horizontal curves, vertical curves, photogrammetry, GPS, you name it. There's a chapter in that book. So what I'd recommend doing is flipping to that, and it's got astronomy in there too. Flip to that area that you're not that confident about, you know, horizontal curves, for instance, and start answering those questions. And not only does it give you the answer, but it also explains why it's the answer. So you have the question, you have your multiple choice, and then below that, you're going to have the solution and explanation. It's called 1001 Solved Fundamental Survey Questions, or something like that. 1001 Fundamental Problems, Surveying Problems, by Jan Van Sickle.
Heather's put that up in a link to that on Amazon in the chat.
Yeah.
And I also posted up Jan's most recent book, which is most reflective of the current exam plan,
Right.
in there as well. And that's Surveying Solved Problems, 5th edition.
I'm telling you, that to me, if you're going to have one book to study with, that should be the book. It's not cheap. When I did it, it was me and another guy. We went in halves on it, and we just kept trading the book back and forth. That's how I did it. I think you can get it for like $170 or something, but I think the list price is like $425 or something ridiculous. But yeah, it's worth its weight in gold, I'm telling you. So that's what I want to say first off, is about a half hour to an hour a night, 5 days a week for about 4 to 5 months. That's what I would recommend. And now you need to focus on what NCES says the exam is going to cover. If you go to NCES, the FS exam, you're going to find where it says it gives you a PDF of recommended knowledge, and it lists out every single thing that you should be studying. And then in addition to that, they're also going to provide during the exam, and you can go get it right now. It's called the equations booklet or something like that. So get your hands on that, because if there's not an equation on that equations list, 99.9% of the time, you're not going to need it. They're giving you every equation that you're going to have to know how to utilize for the exam. That's the whole point of the equation booklet. So go download that. I'm going to share my screen. I have an older copy of it. Can the host disable?
You should be able to.
Okay, let me see. Let me know if y'all see my screen. Okay, can y'all see my screen?
Yes.
Okay.
Can
All
you
right.
can you maximize that so we can?
Yeah.
actually see
Yeah.
it?
I'm gonna get I want to show y'all this booklet first. Yeah, this guy right here. It's called the Reference Handbook, and in this book, it's 12 page. It's a 12-page document, and it lists every single equation you're going to need for the test. So, Kyle, you're worried about photogrammetry? I would focus your effort on understanding the terms and equations that are associated with these equations right here. Okay. I'm not saying you shouldn't expand your knowledge and know a little bit more, but this should be your focus. Knowing how to solve for parallax, knowing how to do scale, Snell's law. Okay, and I can go over briefly some of these, but if you're worried about photogrammetry, come to this reference manual, reference handbook, focus on these equations and these terms, because that's what they're going to ask you on the test. This is a cheat sheet to the exam right here. Okay, it's 12 pages, but the last of it, I mean, it's not really that much, and this is what I focused on to create my manual. Okay, because of that reason. If it's not here, they're not going to ask you about it, most likely. Okay. All right, before we waste any more time, let me get going on horizontal curves. So it is a given. On the test, you will have a double proportioning question of some way, some manner of a double proportioning, which we went over last time. And I guarantee you're going to have a question on horizontal curves. It could be an easy one, could not be. I don't know, but you need to know horizontal curves, okay? And I cannot stress more what Robert already said about having your calculator being very familiar to you, okay? You need that calculator that you use, doesn't matter how simple or advanced it is, it needs to be acceptable during the exam, and you need to know how to use it. You should know where pi is without having to look for it, because that's valuable time you're going to be wasting during the test, okay? All that kind of stuff, converting decimal degrees to degrees, minutes, seconds, all that kind of stuff should just be second nature. And one more quick thing, do not bring your phone in the exam room. I've literally watched a grown man cry when I took my main exam because he brought his phone in and kept it in his coat pocket and hung his coat up at the front of the room. He was, 20 feet away from the phone, and they still kicked him out, and he can never take the exam again, he was told. So be very careful about doing that. I left all my stuff in the truck, so I'd recommend y'all do the same. All right. Horizontal curves. Let me get out of this. Bring this guy up. Okay. Can y'all see me as well? Like if I were to let me see, I'm gonna try and yeah, can y'all see my not my screen, but if you click on my my camera of me, then you'll be able to see downward onto my paper. Is that correct?
Yes.
Okay. All right. Horizontal curves. The first thing is you need to be very familiar with that equations booklet, which I just went over with you. You got to know all the terms. You got to know, what is a length of chord? I'm sorry. What is a chord length? What's the abbreviation for it? What is arc length, radius, and all that? Okay. And then get familiar with the equations. You do not have to memorize the equations. Just get familiar with them. They're going to provide you to all these equations. So don't waste your time memorizing equations, because they're going to give you everything you need. Okay. And then also you got to just step back and think logically here. What is longer, a chord or an arc length? Right? Right. Arc length is going to be longer. So when you're doing your calculations, on the test, just quickly glance at that and make sure that your chord is shorter than your arc length. That's a really easy, quick way to check yourself and make sure. I'm not saying go back through and redo all your math, but if your arc length is 240 feet and you're getting, after you done the equation, you're getting an arc length of 145. I'm sorry, a chord length of 145 when your arc is 140, something's wrong, right? So just try to step back, get your head out of the calculator, get your head out of the numbers, and really just think logically about what you're doing. And that can be applied to everything, not just horizontal curves, okay? Then the first thing I want to go over is this mind-numbing idea of degree of curvature versus your intersection angle or your delta angle, okay? So here's your two radii, and you got your curve. So you got your radius. This is your I. This is your delta. They call it intersecting angle, delta, central angle. There's all kinds of names for it, okay? But then also you're going to see degree of curvature. They just call it a capital D, okay? And of course, you got your arc length, and then you got your chord going here. And then on a regular curve, you're going to have your two tangent lines, okay? So you got your two tangents, your two radii, you got your chord, your arc length, and your central angle, aka delta angle, aka intersecting angle, okay? Those are the basics of a curve. What I want to go over is this degree of curvature, okay? Now, there's two types of arc definitions, all right? The more common term, I just want to make sure everyone can see me. If y'all can't see my paper, let me know. If it's not clear, let me know. Don't let me keep going without y'all telling me. The two definitions are arc definition and chord definition. Those are the two definitions of a curve, okay? They call them curve definitions. One is measured by the arc, obviously this one, arc, and one's measured by the chord. Typically, chords are used, I say typically because there are exceptions, but typically you see chord definitions being utilized for railroads, okay? And I'll explain that in a minute, why that is the case. And then you'll have arc definitions for roads and trails and all kinds of other stuff, okay? Stream beds, all kinds of various items, but typically chord definition is utilized for railroads. And the reasoning is because, we'll get into it. So here's your curve, right? And then you got your radii going to the center. On the arc definition, you're going to use the chord. On the arc definition, you're going to use the arc. Chord definition, you're going to use the chord. The magic number is 100 feet. All right. All right. So I'm just going to, from here on out, I'm going to be talking about arc definition. All right. So the arc definition says that we're going to subtend a curve that is 100 feet long. So from your PC, point of curvature, to your PT, you're going to have a curve, and that curve is going to be 100 feet long, okay? And for chord definition, same thing, but the chord is 100 feet, all right? So if the chord is 100 feet, on this example, it would actually be a little bit smaller, right? So you're going to have long, smooth curves when using the chord definition as compared to an arc definition. Slightly more so, but still it's going to be longer and smoother. And the reason they use it for railroads is because railroads need long, smooth curves whenever they're being built. They aren't like a car that can turn on a dime, right? So you're going to need a long, smooth curve. So they created the chord definition. All right. So let's not worry about chord. Let's just worry about arc. Okay. So they say when an arc is 100 feet long, the angle that it is created right here is called D. all right? The degree of curvature. So you see D here. Now D is going to equal I or your delta or your central angle when the curve is 100 feet long, okay? But not all curves are perfectly 100 feet long. You know, you have a curve that could be 130 feet long, right? Another 30 feet over here. So now we have this right here is your I. I'm going to call it I instead of delta or instead of central angle. From here on out, I'm just going to call it I, okay? So your intersection angle for 130 feet, 130 feet creates an I. But when it's 100 feet, it's creating a D. Now let's do the math behind it, okay? So think of it this way. You have angles and you have lengths. Angles and lengths, okay?
Hey, Dan, we lost your video on
There
yourself.
you go.
Oh, there we go.
Okay. Yeah, someone was calling me. All right. So think about it, a division of angles and a division of lengths, okay? You can have your angles over here, your lengths over here. Now, the formula is the proportional angle of the curve divided by a full circle equals 100 feet, 100-foot section of curve, arc length, divided by full circumference. I'm gonna go over all this, don't worry. Okay? So what this is saying is, you have let's say you have a circle here. And I have my two radii that create an arc that is 100 feet long. This will be my D, because D only occurs when you have 100 foot of arc. But this is a full circle. This curve can extend as long as you want, right? It doesn't have to stop at 100. The car can keep turning on the road or whatever. So if we think of it as angles versus lengths, all right, now let's take this right here. Let's extend it some more. This is going to be my I, and this is going to be 200 feet. From here to here is 200 feet, okay? So if we fill in this formula, you'll see what happens. The portion of this curve, the angle of the curve that creates 100-foot arc length. Okay, so the portion of this curve that creates an arc length of 100 feet is always going to be D, correct? We just went over that. So this is going to be equal to D. Think about it. The portion of the curve that creates 100-foot long length is going to be D. So we have D divided by a full circle, 360, equals 100-foot section of the curve, 100, divided by the full circumference of the circle, which is 2 pi r. Okay, so this angle, this D, is only a portion of the huge circle, and this 100 feet is only a portion of the whole thing. So we have the whole 360-degree angle. We have the whole circle of the whole circumference of the circle. Those are the large parts, the totals, total and total. And then we have the proportional degree, which is that small angle to create the 100 feet. And then we have the proportional length of the arc, okay? Now, if we do all this math, D is going to, all right, D 360 equals 100 divided by 2 pi r is 6.283. We cross multiply, we have D times 6.283 equals 36,000. Wait, sorry, this is still R, 2 pi r. So now from this, we have D times 6.283 times R equals 36,000. From this, we can figure out our D, R, and R. Let's do D first. So if we do D, divide each side by 3.283 R. So D equals 5,729.58 divided by radius. Or we could have solved for R, and R equals the same thing, 5,723.58 divided by D. Now these are constants. This is given to you in the exam. I just wanted to show you the concept of proportionality with this. So to summarize, and this is important, okay? Angles and lengths. Divide this thing into angles and lengths. We have D is to 100 as D is to 100 as 3. Let me see. I'm sorry. D is to 360 as 100 is to the circumference. So we have a portion of 360 and we have a portion of the total circumference. Does everyone understand that? D is to the whole circle as 100 is to the full circumference. And that's what this equation is all about. In the end, it all summarizes into these two constants. And from this, you can determine your degree of curvature or your radii, whichever you prefer. And the same concept applies to the chord. This is all for the arc definition. The chord definition, a little bit different, but it's the same idea. So in this one, you have your arc, radii, and you have your chord. On this one, D is right here. So D occurs in the chord definition when you have a 100-foot long chord. Now this one's easy because you can divide this thing in half and you have two right triangles. And I recommend breaking whatever you have down to right triangles if at all possible. I have a whole section in my manual about right triangles and Pythagorean theorem, sine, cosine, tangent, all that stuff. And that is vital to understanding most things in survey, but especially horizontal curves, okay? So if we take this and we want to solve for our radius again, okay? Well, if you look at this, we got ourselves a right triangle here. And the radius is the hypotenuse of that right triangle, right? So let's just do a sine of this. This angle right here is going to be 1/2 of D, right? If I cut the chord in half, I'm cutting this angle in half too. So D divided by 2, that's my angle. Sine's going to be opposite over adjacent. I'm sorry, tan. No, sine opposite over, no, it's tan. Wait a minute. No. Yeah, I want to solve for R, so it will be sine of this. Okay, so sine opposite over hypotenuse. What is this length here? It's 1/2 of 100, so it'll be 50. So sine of this angle equals opposite over hypotenuse. Opposite is 50. Hypotenuse is R. Okay. So if we do the math for this, I want to solve for R. I would bring R over here. This angle, 50 divided by this angle. So R equals 50 divided by sine of D over 2. That's what R equals. And then if I want to solve for D, I could do the math here, but I want to solve, typically you're going to be asking for R, okay? So that's the chord. And this one's going to be less utilized than the chord, okay? I'm sorry, the arc. So that's my explanation for the relationship of D, degree of curvature, to your intersection. And I'm going to show you an example how we can use this. It might make it more clear, okay? The next thing with curves is understanding that you should be applying ratios or proportionality to a curve. And this is an example of that. Remember, the small portion of the curve, angle of the curve, compared to the full circle, 360 degrees, is to a portion of the arc compared to the full circumference, okay? And then finally, you need to know relationships of angles. I'll get into that right now. So relationships of angles. Okay, so you have this is not something that they're going to give you on the test, but it's in my manual, and feel free to email me. I'll put my email in the chat if you have any questions about any of this stuff, okay? So you got your tangents. You're going to have your intersection angle. You're going to have your external ordinate and your middle ordinate. When I mean by relationships of angles, you should be able to know what angles equal each other in this figure. Okay. So right here, this angle right here, that is your deflection angle. Okay. The deflection angle is from your chord to your tangent. That's your deflection angle. You might not know the value, the actual degree of this curve, but what you should know is, let me see. You should know that it's half of your intersection angle. So if your intersection angle is 40, your deflection angle is going to be half of 40, which is 20. So if this is 40, this is 20. This is 100, this is 50. Okay. I didn't draw this to scale, by the way. So just so you know that. All right, so your deflection angle is half of your intersection angle. That's one thing you got to memorize. Something else. Your tangent right here, when it intersects with this tangent, this forms an angle, and that angle is I. This angle equals this angle. So if you take two tangents and you intersect them, that angle is equal to this angle. The next thing you need to know is this right here. Actually, no, let's not know that yet. Should have drawn this better, but this right here and this. So from your radius to a tangent is going to be 90 degrees always, okay? So the angle between your tangent and a radius is 90 degrees, and that's why it's a tangent line. That's what a tangent line is. It's a line that intersects a circle at one point, right? So if I were to draw from the center of that circle up, it would hit it at a perfect 90 degrees. A tangent line is a line that intersects a circle at one point. If it goes a little bit too far in, it's going to intersect it at 2 points. Okay? It needs to intersect it at just 1 point. And when it does that, it forms a 90-degree angle. And that happens anywhere along this curve. Okay? So, radius to tangent, 90 degrees. Well, think about it. If this is 90 and this is I divided by 2, then this is going to be 90. Well, yeah. So we can chop off, if then this is a line. So from here to here is 180 degrees, right? 90 of it's gone. So now we only have 90 degrees to go from here, from the tangent, all the way to the radius. And we know I divided by 2 is for this portion. So for this angle, it's going to be 90 degrees minus I2. Okay? The line from where they intersect up here, this is called the PI, where they intersect, where the two tangents intersect all the way down to the center. That line, it's going to intersect the chord at 90 degrees on both sides. Okay? So that's perfectly perpendicular to your chord. So these are all 90s. So there you have it. There. Oh, yeah. So we got, and it's a mirror image, obviously. So, let me see. This angle right here, this would be 180. This is 180 minus I. Right? So you have this angle right here is 180, and we know this is all taken up by the angle of I. So let's say I was 60. We knew from tangent to tangent is going to be 120, right? 180. The I is 60. So it'd be 120 left minus 60 equals 120. And we know it's split in half. So this is 60 and this is 60. Okay. Let's see. So that's what I mean by relationships of angles. And you can solve a lot of problems knowing these angles and how they relate to each other. Because on the exam, they might be asking you for this angle, the deflection angle, and they only give you the intersecting angle. Well, now you know that that is 1/2 of I. So if they give you that this is 90 degrees, you're going to know that the deflection angle is 45. Okay. So if you're going to spend your time memorizing something, I would memorize this and how they all relate to each other. Okay. This equals that. These are 50% of I minus 180. These are 90 degrees. These are 90 degrees. This is half of your delta angle. This is 90 minus half your delta angle, okay? So get all that memorized. Takes 10 minutes, commit it to memory, and it's going to take you a long way on the test. I guarantee it, all right? All right, let's go quickly into a problem, and I'll break it down, and my problem is going to show you relationships of angles, how it's important, and what I mean by proportionality or ratios, all right? All right, so let's say they give you three knowns. Let's say they say you have a curve, the radius is 700 feet. Your intersecting angle, AKA delta angle, AKA central angle, equals 60 degrees. And your PC stationing equals 1320. Does everyone understand stationing? If you don't worry about it. All you got to do is scrape away the plus sign and you have your answer. Stationing of 13 plus 20 is 1320. Okay, 1,320 feet. This is dealing with like road alignments, pipeline alignments, all that, and alignment. All right. Don't let it confuse you. Just blow out the plus sign and you have your number. Okay. For this example, let's keep it. All right. So these are our givens. This is what they give you. They want to know what is the length of curve at station 14 plus 50. And they also want to know what the deflection angle at that will be, okay? So these are the two things we got to figure out. Arc length, length of chord and your deflection angle at that station. So what we got here is a curve. Draw out what we know, okay? Here's your curve. This is your PC. This is your PT. We know we have a radius of 700 feet. We know the stationing on this curve right here is 1320. Okay. Somewhere along this curve is stationing 1450. Okay. Somewhere along that curve is station 1450. I know that my entire angle here is 60 degrees. Okay. The question is, it wants to know the length of the chord from PC to station 1450. And it also wants to know what that deflection angle is right there. Those are the two questions. How long is the chord from your PC point at 1320 to station 1450? And what is the deflection angle? And deflection angle is from chord to tangent, okay? All right. So, let's fill in, that's all they gave us, but let's fill in some more stuff here. From our relationships of angles, we know a lot of stuff. We can figure out all kinds of other angles here, okay? Let's not get crazy and start labeling them, but I know that I can figure out this deflection angle. I know that from here to here is 30 degrees, right? Because that's half of I. I know this is 90 degrees. This is 90 degrees. I know if I were to cut this in half, this would be 90. This would be 90. This angle right here is 60 degrees. Okay. That's all from our relationships of angles memory. All right. Let's not go down the road. Let's just figure out what we need and then go from there. Ratio. What do I mean by ratios? Well, the arc length from my arc length from the PC all the way to 1450. So let's do this. So I have my length of chord divided by I equals my arc length of this whole arc from PC to PT is going to be to I as my arc length of curve up to 1450 as the angle up to 1450. And what do I mean by this? This length is to 60 degrees as the smaller length is to this angle. Okay? The total length is to the total I as the shorter length is to the shorter angle. So I'm making it a ratio here. I got my totals here, the total length compared to the total central angle is to the portion of that angle length divided by the portion of the angle. So if we plug in the numbers here, we're going to be able to solve for what we need. We know this, we know I is 60 already. They gave us that, but we don't know L. So we got to solve for L to figure out this portion of the equation, okay? And I'll show you how we know this already here in a second. It's easy, just normal subtraction, but I'll show you. So first let's solve for L. The equation for L per the exam manual equation sheet, L equals radius times I times pi divided by 180. That's the equation for length of a curve. We have R 700, we have I 60, pi is a constant number, and then 180. So L equals 700 times 60 times pi divided by 180. That times that times that, L comes to be 733.038 feet. All right, here's a logical check. Remember, arc length should be larger than radius, right? I got a radius of 700, so my arc length better be larger than that. Wait up, does that make sense? No, that doesn't make sense, sorry. Trying to think of a way to check 733. Oh, we could compare it to the chord, but we don't know the chord yet. So let's keep that number in mind. We'll make sure that it's smaller than the chord. I mean, sorry, larger than the chord, because a length along a curve should be longer than a straight line as the crow flies, right? So my length is my length of the whole curve is 733.038.
We lost your video again, Dane. There you go.
You see it? Okay. Let me plug my phone in, make sure it didn't die. Give me a second here. Okay. Can y'all see it again? Y'all all good?
Yeah.
All right.
If you can zoom in at all, that'd make it easier to see the numbers.
Okay. Let me see. I don't know how to do that. Yeah, I don't see it. I don't know how to do that. Sorry.
Okay.
If anyone knows how, let me know. Okay.
For your flying height.
Well, I have a I don't know if you see it, but I built a little stand here. So I need a saw to cut it. All right. All right, so we know L now and we know I. So let's start plugging this stuff in. So 733.038 feet. I is 60 degrees equals, what is my arc length of the curve up to station 1450? So I'm starting at 1320 and I go along the curve to 1450. It's just simple subtraction. 1450 minus 1320, right? So, let me see. Yeah, so it'd be 1450 minus 1320, 0, 3, 130 feet. So the arc length of my curve up to that station is 130 feet. The last thing I want to figure out is my degree, my angle that is created up to 1450. And I don't know that. That's going to be my, what I'm solving for here. So if I do the math here, let me see. If I do the math, y comes to equal 10.64. 733.038 divided by 60 equals 130 divided by y. Solve for y. Y equals 10.64 degrees. So, of that 160 degrees of the whole curve, only 10.64 degrees is needed to create the curve up to stationing 1450. So now I have my y, okay? So now if I have y, let me rewrite this. Redraw it here. So this whole thing was I. This is what I just figured out as y, which is 10.64. This was 60. Here's station 1450. Here's station 1320. I have my chord here for just that portion. And I'm going to have my tangent. I want to figure out this angle. Well, from our relationships of angles, I know that this is 1/2 of this. So if this is 10.64, I know this deflection angle will be 5.32 degrees. So that's one of our questions. What is the deflection angle that's created when you go up to station 1450? Well, the answer is 5.32. I didn't even have to do any math for that. That's just knowing my relationships of angles. The next question was, how long is this chord? Okay, well, the equation for length of chord is 2 2r sine of 1/2 your d your delta angle or intersection angle. Okay, so let's start plugging in our knowns here. 2, the radius never changes. Radius is always going to be 700. No matter what part of the curve you're on, your radii is always going to be 700. It's the same curve, just different lengths along the curve. So radius is 700. Then you're going to have sine I divided by 2. We found I to be 10.64. And we know half of that is 5.32. So length of curve, if you do this math, it comes to be 129.81 feet. So my length of chord from PC at 1320 to station 1450 is 129.81 feet. Now that is something we can logically check. This should be a little bit shorter than the length of curve. Length of curve, we said, was 130 feet. That is a little bit smaller than 130 feet. Okay, 1900ths actually. So this checks out as a viable answer. Okay, and that is the answer. So 129.81 and 5.32. So this, the real takeaway of this problem is knowing the relationships of one angle to another in a horizontal curve setting. And then the other thing is the ratio or proportionality of a curve. And again, let's focus on that. So you have this long curve from PC to PT. That whole curve, we're going to call it L. L is to the whole angle, I, as a portion of that curve. Let's say this is called X. X is to a portion of the angle creating that curve, Y. The whole thing, the whole arc length is to the whole angle as the portion of the curve is to the portion of the angle. And that's right here. Does everyone understand what I'm trying to get at here? Okay. If you go back to my screen that's sharing right now, I'll show y'all my manual and what I mean by these and how I have them all outlined, and then we can go on to photogrammetry, okay? So here's horizontal curves. This is just a takeaway from the manual. I'm sorry, from the equation sheet. Defines everything and identifies them up here. This is the whole the equations that they provide on the exam. I've rewritten them here. This is my relationship of angles, showing you what equals what here. So, and I explain it all here. Oh, another thing I want to just jog y'all memory. Remember, intersecting lines, it creates 4 angles, right? Opposing angles are equal to each other. That's very useful knowledge at times during the exam too. Okay, don't forget that. Then I go into how the curves are described, arc definition versus chord definition, what that means. And I show you how to derive, or I show you the relationship of a curve angle and a degree of curvature, which is what we went over in the beginning. And then I show you this whole proportionality thing, okay? The whole circle is to a portion of the circle as the whole circumference is to a portion of the circumference. And that's the idea of having angles and lengths separated yet equal, okay? And then the chord definition here, and then I have some example problems. Rob, you mind if I just go into photogrammetry real quick?
Yeah, we're just a little after 5. So if people want to stick around for photogrammetry, that first diagram you show right there is exactly what I was talking about. Just zoom in up the upper controls of the, there you go, a little more. Fill that screen up. Yeah.
All right. So my photogrammetry is limited to the discussions of photogrammetry I have limited to what the equations are on the test. I gotta go, baby. You gotta come on. I'm sorry. I know. Sorry, my son. Okay, so let's talk about scale, I guess, first. Yeah, so what I wanted to say was this is limited to what I think is going to be on the test, okay? So you don't need to be a photogrammetrist or a licensed photogrammetrist on the test. They're going to be basic, this can be questioning basic questions, okay? And understanding what these lengths mean. So you have your image or your sensor. So let's say you have a picture, okay? Let's say you have a photograph of the ground. Okay, so here's your photograph. And you got all your stuff here, okay, on your picture. They call it a sensor because sometimes it's on the plain digital camera, okay? But that picture is really taking a picture of a large piece of Earth, right? So kind of like with horizontal curves, a lot of photogrammetry is going to be proportionality and ratios, okay? So the distance from this point right here to this point right here, let's call this A, let's call this B. If you were to find that on the ground, point A and point B, obviously, the real life ground distance is going to be a lot larger than the picture distance. It's going to be scaled way down in the picture. But the idea of scale is that distance compared to this distance, you can use that scale to apply to anything else. So if I know this distance is 1,000 feet, and I know in the picture it's 4 inches, okay? Well, you want to keep your units the same. So 4 inches equals how many feet? Equals 0.3 feet, right? So 0.333 feet is to 1,000 feet as, let's go from point B, point C to point D now, C to D. Let's say that distance is unknown, but on the picture, we know the distance is 3 inches, let's say. 3 inches. So if it's 3 inches in the picture, which is 0.25 feet, right? How many feet on the ground will that be? Let's do the math.
You couldn't have made it easy math and said it was 3 inches on the photograph, could you?
Yeah, I know. I'm trying to find my calculator now. Hold on. All right, so 3.333 divided by 1,000. That's going to give me my scale factor here. 0.3333 divided by 1,000. 0.000333 equals 0.25 divided by x. 0.000333 x equals 0.25. Solve for x. Be 0.25 divided by that, so store 1. So 0.25 divided by, recall 1, 750 feet. Okay. So that's almost the exact same thing as that curve proportion that I just did. The whole thing on the picture divided by the whole thing, the whole thing on the picture divided by the whole thing on the ground is equal to the portion on the picture divided by the portion on the ground. Okay. You just got to keep everything in line and it's going to turn out. So that's the essence of scaling with photogrammetry. And they have fancy ways of saying it, you know. So what they do, you can also figure out this scaling with heights. Okay. So think about this as horizontal distances. You got horizontal distance on the ground, horizontal distance in the picture. Well, the same thing applies to vertical distances. All right. Let's take the same exact situation. You got your picture and you got your big ground, right? So what it's saying is this picture is created from a camera, this camera right here, okay? This picture creates a camera. I'm sorry, the camera creates a picture. And the way that works is a thing called, I don't know the science behind all this, but it's the focal length. So inside your camera, you're gonna have a distance from the sensor of the camera to the picture, okay? That's called your focal length. So this distance right here is called your focal length. That focal length is going to be proportional to the distance from the camera to the ground. And that is called height. So you have your cameras inside the airplane and it's flying at 1,000 feet off the ground. Okay. That is called your height. That's the height of your camera. And then that is proportional to your focal length, which is the distance in your camera sensor to the image. All right, let's make that 0.33. It's only 4 inches long from the sensor to the image. Well, if I did the same math, 1/3 0.33 is to 1,000 as, let's raise, if I do this, it's going to create my scale factor, that 0.000333. That's my scale factor. Now I can apply that to a length on the picture, or I can apply it to a length on the ground if I know that. If I know the length on the ground, I can figure out how far they are in the picture. Or if I know how far they are in the picture, I can figure it out on the ground by using my focal length divided by my height. Okay, so those are the two ways to scale.
Hey, Dane.
Yeah.
Let me jump in here real quick.
Yes.
Everybody noticed that he's dealing with 1,000 feet as a flying height or as a distance on the ground, and he's taking that inches of either focal length or distance on the image or the sensor or the film, on the diapositive, if you want to get into technical terms. And he's converting it into the same units. And that's key. Well, that's one of those things we call a unitless ratio.
Yep.
And other times you'll see scales expressed as 1 inch equals 50 feet or 1 inch equals 200 feet. And those are not unitless ratios, but you can convert them to unitless ratios by doing the math.
Yep. I recommend unitless. I always say convert, just get everything on the same page. Convert all your inches to feet. Convert all your grams to kilograms. Convert all your wavelengths to wavelengths. Whatever the unit is, get them all on the same page. That's my strong recommendation. It'll clear up a lot of, it takes a few minutes to convert inches to feet. Go ahead and do it. Divide your inches by 12. Bam, that now you have your feet. It just cleans up a lot of stuff.
And just be aware of that if you get to the answers and the answers are in 1 inch equals so many feet.
Yeah.
If you're in a unitless ratio, as a
You're gonna have-
logical distractor, one of those unitless ratio numbers could be what you're looking for, but in a answer that should have inches equals feet.
Yeah, no, you're definitely right. What if the answer, what if they asked for, they gave you the ground distance from A to B, they gave you the picture distance from A to B, and they gave you the picture distance from C to D, and they said how many miles is D to C on the ground? Well, I know it's 750 feet. They might give you that as one of the answers. They might say 750 miles as one of the answers. And if you don't convert this to miles, you might select it. So Rob's right. Just be careful of units. I personally like to get everything on the same unit at the beginning and then check it on the back side. When I say check it, I mean convert it back to whatever you need. Hopefully it's in that same unit. You don't have to worry about it. But no, you're definitely right to bring that up. Thank you. All right, so that's scaling in photogrammetry. That's pretty easy stuff. I mean, that's just common sense and knowing how to ratio. Okay. Let me see. Let's do the lens equation. Lens equation. Can y'all all see my diagram here? Okay. The lens equation compares the ratios among object distance, image distance, and focal length. So you have your object. You have your object here. You're going to have your camera lens. You're going to have your focal point. And then it's going to, on the back side, it's going to create an image, okay? The important part here is this all creates a perfectly straight line from the center of your lens, from the object to the center of the lens to the focal point is all a perfect straight line. And the image is going to be inverted, okay? When I say focal point, I don't know camera science, but I think of focal point as maybe your sensor. So I'll call it focal point because that's what they call it, but it could also be like maybe the sensor. I'm not really sure. But from the focal point to the center of your lens, that's going to be your focal length, or F. Okay. The object distance is the distance from your lens to the object. That is O. And then finally, you're going to have your image distance. Now, the image distance is the distance from your lens through the focal length to your image. This is going to be called your image distance. That's the distance from the image to the lens. Your object distance is your object to the lens. And your focal length is going to be from the focal point to your lens, okay? So there's your three elements. This is the lens equation, okay? And all the equation says is the inverse of your object distance plus the inverse of your image distance equals the inverse of your focal distance. Okay? There's really no further explanation needed. All this is saying, all this lens equation is saying is the inverse of your object distance plus the inverse of your image distance is going to equal the inverse of your focal length. Okay? So on the exam, they might give you your image distance and your focal, and they're going to ask you to solve for your object distance. Okay? Again, don't ask me the science behind this, but this is the lens equation. Okay? Let's do relief displacement. Okay? If you look at my image here, you'll see that, all right, first off, well, before I do this, I want to do parallax first, okay? Now, parallax sounds like a pretty hard concept, but a really good way of figuring parallax out is, I want y'all all do this right now if you want. So I want you to stick your thumb out as far as it can go and cover up something on your wall or a light or something like that with your thumb with one eye open. Okay, so close one eye, put your thumb far out, cover up something in the room. Then close the eye that's open and open the eye that's closed. And you're going to see your thumb move, right? With your arm extended very far out, it's going to move a little bit. Now, if you bring your thumb in closer and do the same thing, close one eye, open it, and then do it again. You're going to see when your thumb is close to your face, it moves across the wall or across the ceiling or wherever you're pointing your thumb at. It's going to move a lot. The distance is going to increase, okay? That is the concept of parallax, all right? So if you, the concept behind this is the closer the object is to the viewpoint, the greater the shift will be. All right, so the closer the object is to the viewpoint, which is your camera or your eye, the greater the shift will be if the viewpoint is shifted. I'm sorry, the greater the shift will be if your viewpoint is shifted. So where this comes into play is you have a plane. You have a plane flying over the ground, right? It's going from left to right, flying. And it's going to be taking photographs. Takes one here. And it's going to take another one here. It's going to take another one here. Okay? Let me see. Let me think. And then it's taking, so on the ground, it's going to look like this. Right? Let me get my bearings straight before I mislead y'all. Let me think. The further away the object, the apparent shift is smaller. Okay, the apparent shift is in the same direction as the motion. Oh yeah. Okay. So when you have your thumb extended far out and you close one eye, open the other, imagine that being like the shutter of the camera on the plane. So if you're not an alien, your eyes should be horizontally along the ground, right? So when you close one eye and move it, your thumb looks like it's moving across the wall, not up and down, right? So imagine your eyes as the shutter of the camera on the plane. So as it's moving along the earth, the parallax, the change in the viewpoint occurs the same direction as the flight of the plane. Just like you change your eyes from left to right, your thumb moved left to right. If you were to turn your head on its side and do the same thing, your thumb would move up and down. It's because that's the direction of your eyes, okay? So in the diagram below, it is assumed that the direction of motion is along the x-axis. Thus, no parallax will be observed along the y-axis. So when you're looking at the wall with your head straight up, your thumb does not move up and down. It's staying on the same line as your eyes are, right? It's not moving up and down. If you turn your head sideways, it's going to move up and down and left and right, right? It's going to shift downward and left and right. So when the plane's flying, you can assume that the parallax is along the motion of the plane and nowhere else, okay? Now that's not necessarily not necessarily true. The plane could be flying at an angle and all that stuff. But that's the objective, is to have the camera nice and flat, moving on a horizontal line parallel with the ground, okay? The equations for parallax are provided, and the equations are pretty straightforward. So parallax is equal to x minus x of 1. So if we have the change on the ground, which is x, capital X, is going to be equal to the change in the photo, which is the small x. Okay, so you got your picture x minus the next picture x. So you have one photograph is x, the next photograph is x1, the next 2, x3, as far as you can go, okay? And that's what the equation is. It's the change in distance along the motion of flight, the distance on the image from one image to the next. So if this distance is 5, this one is 5.5, it's going to be parallax will equal negative 0.5, okay? Does everyone understand the concept of parallax? Do I need to go further? Okay. I'm not reading chats and stuff, by the way. I don't know if I don't want to switch back. I don't want to mess anything up, but so maybe I can unmute if y'all have any questions.
Yeah, no comments on the chat.
Okay.
Except earlier was on the horizontal curves was something that said this is helping explain curves. So
Well, that's good, I guess. Yeah.
You know, I think one way to another way to envision parallax is if you take your whatever you may be drinking this evening, a can of Coke or a glass of water or something more adult, and put it on the floor and stand directly over it. And this also relates to what you're going into next is the displacement.
Yeah.
Is look straight down on the top of that. And then as you move your head off center, move yourself off to the right or left, you'll see the base of the drink and the top of the drink. And that's where you're going next with the horizontal displacement from photogrammetry.
Yeah, no, yeah, you're right. Yeah, that's a good, I never thought of it that way. You can still, yeah, you can't see the base if you're directly over it, but you can if you move from side to side. Okay. Let me do Snell's law, then we'll go to displacement. Snell's law is pretty easy. All right, so this is what happens whenever you're like scooping leaves out of a pool and you have your pool net and you stick it below the surface of the water. If you look at it, it looks like your pole is bent, right? It looks like the pole for the net has a kink in it or a bend. And the reasoning for that is Snell's law, okay? And all Snell's law says is when you change a medium, you're going to change the angle of light. So the medium in the pool scooping net is this concept. So you have air, which is on top of the water of the pool, and you have water, which is in the pool. And when that pole crosses that barrier of air and water, it's going to look like it's bent. And the reasoning is because water reflects light differently than air does. Okay. Now this is a whole physics science too that I'm not going to get into. The concept you need to know here is you're going to have an index value and you're going to have an angle. Okay. So, let me see. So the index value, that's a given constant. Water has an index value. Olive oil has an index value. Liquid mercury has an index value. Any medium, you can derive an index value. Thank God we don't have to figure that out. It's always going to be provided to us. Okay. So you have these index values, and those index values determine the angle of refraction of light. Okay. So what you have two types of light. You have incident light, which is the light going into the medium. And then you have so let's take this like the pool situation. You have air, so you have light coming in, and the second it crosses that medium barrier, it's going to be refracted, and it's going to have a different refraction angle, okay? And all Snell's law states is you have your index value times sine of your angle in that median is going to equal the index value of the other median times the sine of its angle of light. Okay, so the equation's pretty simple. Index times the sine of the angle equals index times sine of the angle. And if you notice, once again, it's all about ratios. The index value of median 1 is to the sine of the angle created in median 1. I'm sorry, index value of median 1 times the sine of the angle of light in median 1 equals the index value of median 2 times the sine of the angle created in median 2. Okay. And that's all that Snell's law states. Again, we don't need to worry about finding the index value. They're gonna provide that to you. And then they have to give you one of these other angles too. But once you have those two index values in one of these angles, you can figure the other one out by algebra, right? So that's Snell's law. Then let's go back up to displacement. So if topographic features are captured with imagery, the further they are from the center of the image, the more distorted. they will appear. Additionally, the taller the feature, the more distortion. So like Rob was saying, that cup, that's dealing with height, but it also occurs, well, no, yeah, no, that's not necessarily true. All we're talking about is height here. So the displacement increases radially outward from the image. Oh, no, it is horizontally too. I'll get to that. So relief displacement is D, radial distance from the image center is R, height is H, and then altitude is capital H. Okay, so let's take, we have our image again. It's taking a picture of the ground. So we have our picture and we have Earth. Okay. So we have the center of our picture. Let's have the center of the point in the picture on Earth. Okay. This applies to that. This applies to that. This applies to that. And that applies to that. So now we have our cone essentially. Okay. Let me see. So, and oh yeah, now we have, so from our image center to our ground center, that distance is H. Let's say we have a building here on the ground. That distance is little h. And then radius is the distance of that building from the center. Okay. So the best part of this picture that you took of the ground is the perfect center of the picture. As you move away from the center of that picture, radially speaking, it gets worse and worse and worse. Your displacement gets worse as you approach the edge of the image. The best it will ever be is in the center, and it's going to get more and more displaced and more distorted as you approach the edges. So if this building is way over here on the edge of this image, that's a lot worse situation for displacement than if the building were here. If it were here, it's like what Rob was saying. You won't even see the bottom of the building. You're just going to see the perfect roof. If you were, the picture of that building, if it were in the center, would look like this. Okay? The picture of the building, if it were towards the edge of the image, would look like this. You would clearly see the base. So that distance from here, horizontally speaking, to here, that is your displacement. Does everyone understand? So you got your building roof of this skyscraper, let's say. So this is the ground. This image, this point right here should be perfectly on top of this point, but it's not. That right here is your D. That's your displacement. It's quite significant. So in the picture, you're trying to find the base of the building. Well, you're going to have to go to the physical base, as opposed to if it was perfectly on top, it would look like that, you know, like that and the base would almost be right on top of each other. Okay. It doesn't just happen for buildings. It happens for mountaintops. It happens for trees, telephone poles, fence lines, everything you can imagine. So if you're trying to find the intersection of a fence as the perfect corner of a property, you might have a situation like that. So you're trying to find the base of this fence. Well, you better go here, not the top of the fence, okay? So the equation for displacement is your radial length times the height of the object divided by the height of flight. Again, D equals the radial length or the radial distance in the image from, and that's going to be from the center to where you are in the picture. That's R, times the height of the feature you're looking at. Let's say it's a 2,000 foot tall building. That'll be 2,000 divided by the height of the camera at the time, the height of the focal point of the camera. I'm sorry, the height of the lens of the camera at the time of flight. So all that's taken into account whenever you're trying to find displacement, okay? Again, you don't need to be a physicist or a licensed photogrammetrist. You just have to understand the basics of this, okay? I would not get nervous or start buying photogrammetry manuals. They just want to know the basics, okay? If you were going to photogrammetry school, they just want you to know the remedial concepts, okay? Just keep that in mind. Surveyors aren't experts at all this stuff. They just understand it, all right? Was that it with photogrammetry? I had one more thing, I think. Oh yeah, curvature and refraction. This one's to be honest with you, this is something that gives me trouble. I have a really hard time trying to understand the concept behind this. I know, I mean, I had to dive pretty deep trying to figure this out. And we only have a few minutes here, so I'll make it quick. But if anyone wants to take like a screenshot of this before we go, it's right here. Okay, so curvature. So this is dealing not really with photogrammetry, but this is dealing with like let's imagine a total station. Okay, so you have your instrument and you're trying to measure a distance from one point to another on the face of the earth. All right, so you have your gun set up here on point A, and you're trying to measure to point B, okay? Now, normally, whenever we measure with total stations, we're doing 300, 400, 500, 600 foot long shots, right? Well, what if you did a shot that was 20,000 feet? I'm not saying you can, just hypothetical here, okay? Well, if you did, you would have to apply curvature of the earth in a shot like that, because over 20,000 feet, you know, like 4 somewhat miles, you're going to have some earth curvature, right? I don't know if y'all ever been to the ocean or I remember seeing this when I went on top of Sears Tower. I was amazed to see the earth. You can actually see the earth kind of curving, you know, when you're at that height. Obviously when you're in a plane too, but just to be in a building and be able to see the earth curve, it kind of gives you perspective on how it's really a concept that you need to incorporate into your survey measurements. But so the earth, you know, you have a curve whenever you measure in between A and B, right? So if you were getting an elevation on this point, let's say this is not a total station, let's say it's a level, okay? And you take a shot, well, your line of sight is perfectly horizontal. And whenever you take a shot with your stadia rod here, the measurement you get is technically going to make the point appear lower than it really is, right? You would measure, let's say 4 feet right here. Well, in reality, it's not 4 feet. It's going to be a little bit less than that, right? Because we have this that we're trying to compensate with curvature. Does everyone see that? And then also, not only do we have Earth curvature, all right, and so the concept there with the height thing, before I move on, curvature will produce higher height readings. So this point will appear to have a higher height reading than it should because of Earth's curvature. All right, so we have curvature to deal with, and then the next thing is refraction. And refraction is the bending of light through our atmosphere. So as your eye is seeing a far distance, that light, the further you look out, the more medium, the more atmosphere that light has to travel through. And light is going to get slower. Think of it as getting slower. I'm not sure if it is getting slower, but think of it as the light moving slower and slower and slower the further you look out. So the further you look out, the more distance creates more refraction. As opposed to you just looking 5 feet in front of you, refraction is minuscule. But if you're looking 20,000 feet out, refraction could have an effect. All right. Refraction error, line of sight accounting for a downward bending of light. Refraction will produce lower height readings. So I said that you're looking perfectly straight out earlier, right? Well, in reality, you're really looking a little bit bent downward. So it's going to give you readings that are lower than it should be. And the reason curvature and refraction are typically combined in trying to figure out error is because one counteracts the other. The error you get with Earth curvature is balanced out by the area you get with refraction. So one makes it worse, one makes it a little bit, I don't know about worse and better, but they're in opposite directions of each other. So the further you go, the more curvature. The further you go, the more refraction. And actually, they help counter each other out, okay? The equations that you need to know are right here. And this is all that they really have on the equation sheet. They're going to give you the correction of curvature and the correction of refraction. And then you're going to have to apply this constant here. I'm not sure how to derive this constant. All I know is that it's the constant. And what this constant is the relationship of refraction to curvature. That's 0.0206. That's the relationship of one to another. So over a length of 20,000 feet, refraction is X, curvature is Y. The relationship between the two is going to be our constant. Okay. Again, don't worry about being an expert. Just know that that's why this number exists. It's just a constant that is given, showing the relationship between curvature and refraction. From that constant, we can solve for one or the other. We can solve for curvature. We can solve for refraction. If we know the relationship between the two, and they give us one, well, we can use that to figure the other one out, right? Or vice versa. We know Y, we know the relationship, we can figure X out. Okay. So that's my quick rundown of photogrammetry. If you notice, guys, in almost all of these, it's almost always ratios and proportionment. That was the case with double proportioning, single proportioning. It's the case in horizontal curves. It's the case with scale factors. It's the case with photogrammetry scales. It's the case with the lens law. It's the case with Snell's law. So I highly recommend that you get yourself in a position where you can truly, with just second nature, be able to navigate around a ratio. The total length divided by the total angle equals a portion of the length divided by a portion of the angle. Okay. Same thing with photogrammetry. The length of the, let's see, length of the distance on the picture divided by the length of the distance on the ground equals the length on the picture divided by the length on the ground, right? So again, ratio. Same thing with single proportioning and a subdivision. You know, you have these lots. They're supposed to be 100 feet wide. You go out there and you measure this one. The plat says it's 100 feet. You go out and you measure the distance from here to here, and you measure it to be 99.2. Well, ratio it. The record distance is supposed to be 200 feet. And you want to reestablish this lot line right here. So the total record divided by the total measured, I'm sorry, 199.2. Total measured. So total record, total measured, total measured, total record divided by what you want divided by a portion. So a portion of the measured divided by the portion of the record. So I got my measureds here. I got my records here. If I do this math, I can solve for X, which will be my portion of the measured, which will be this distance. Again, a ratio. All right. It's 7 o'clock. I should probably stop and ask if y'all have any questions. Let me know. I'm gonna stop sharing so I can maybe see y'all screen again.
Sounds good, Dane.
I don't even know how to stop sharing, honestly. So
Do it for you.
This is where we call for help from Heather.
yeah. Oh yeah.
There you go.
There you go. Thank you.
I saw Kent raised his hand.
Hey guys, it's a question kind of regarding the curvature sort of thing. So I got my video set up here, sort of, so we can maybe this will work. No, I'm just new to this. I just did my field course in surveying here about a month ago, and I got more questions and answers after I'm done it now. So to see your curvature stuff, let's say I've got a point here. And I want to make a parallel or a perpendicular line from this road. So I set up my gun here. I got my helper to come out and just create a point here, zero my gun, crank it, and set up my second point. How do I find this? Do I have to set up again on each corner and measure these angles? Or can I do it all in one setup?
That would be,
You can do it from there.
yeah, definitely from there.
Yeah.
Let me see. So it's a triangle. You know, the three angles of a triangle need to equal 180, correct?
Right. Yeah.
And it's a straight line between the first point and the second point. So if you have, let me see. If you have you will know the angle at your instrument, right? So
Right.
that's going to be a given.
Total angle.
So we know,
And
all right, let's just hypothetically say that your angle at your instrument is 70. Just hypothetical, okay?
Okay.
So this angle equals 70. You want to find A and B. I know that I only have 110 degrees to deal with, okay? So A
Okay.
plus B is going to equal 110 because A plus B plus instrument angle has to equal 180. That's just the rule of triangles, right?
Right.
Now, I'm going to need something. Okay. And you know this distance. Let's say this distance is 205 feet, hypothetical, okay?
Okay.
So, and we know this, now this is going to be a right triangle, correct?
Yep.
So we know this is 90. Help me out here, Rob. Do we need another? Oh, we're gonna
Law
know
of
the
cosines, I think. But
Yeah.
yeah, this is one of those ones that I said, yeah, email these into us, and so we get these ahead of time, so we don't look like knuckleheads trying to scratch this out.
Yeah. No,
Sorry, guys.
That's all right.
No,
That's
no,
all right.
no. No, it's fine. So I have in the book, I have a whole chapter on breaking these angles down. And this is going to be a law of sines here. I might need another distance. Let me think. Where is this?
If I could
Oh,
toss,
yeah.
if I could toss in a comment,
Yeah.
when you put that other line in there, you're making that perpendicular to the baseline, correct? So because you're making that perpendicular to the baseline, that's a right triangle. And you've got the other angle at one other end, go to the left, there, and then you've got that length. So you've got two angles on the side, you can solve that triangle as long as you have three parts to a triangle. And at least one of them is a side.
Yep. Can y'all all see my, I'm not sharing anymore. So what we have
go for
here
it.
is, we're going to know this distance too. Let's say this distance is 500 and let's make it 500 feet even. Okay. So I have two sides and an angle. Two sides and angle. So let me see.
You don't need to know that long side, not as long as you know the two sides of the triangle coming out from where the instrument is.
Oh yeah. Yeah, that's true.
Because you've got the angle there and you've got the two sides.
Yeah, let's make this 300. Yeah, so this is going to be a side, angle, side is what this is going to be. You have your one side here, and your angle. And this is written as, just as it's displayed, side, angle, side. See that? So the way you solve for side, angle, side is the first thing you do is law of cosines. The next thing you do is law of sines. And I'll walk you through this. And then the third is summation of angles. All right, so let me go down here. Okay, so law of cosines is c squared equals a squared plus b squared minus 2a times b times cosine of c. All right, I'm going to make this c, and I'm going to make, so this is c, little c. So always the angle opposite the side is going to be your angle opposite the side is going to be direct to each other. So if this is angle A, this will be little a, this side. If this is angle B, this will be little b, okay? So I have C here, and I know C is 70. So cosine is 70. I know, so C squared, which I don't know, equals A squared, which is 300 squared, plus B squared, which is 205 squared, minus 2 times 300 times 205 times the cosine of 70. So if I do all this math, I'm going to figure out what C equals. All right. And does anyone want to help me try to do this so I get the right number? So 300 squared plus 205 squared, store 1. Okay, so I got 70 cosine times 205 times 300 times 2. Yeah, I'm messing up. 300 squared. 90,000.
So without without dealing with all the formulas and such, if I had my trusty programmed HP, I would just set it up as a
Okay. And that, so I get 10,520, no, 105,214.26. That equals this distance right here. And that, if you think about it, that's going to be pretty right, because we have a 70-degree angle is pretty close to being 90, right? So we got 205 here and we got 300 here. The distance between them is going to be pretty far because that angle is huge. All right. So now I have my C. Now law of sines states this is where the distance of A equals sine of A equals distance of B equals sine of B, angle B equals distance of C sine of C. Okay. So there, all it's saying is this, again, ratios. This is to this angle as this, I'm sorry, as this is to this angle as this is to this angle. Okay. So let's just take, we don't need to do them all. We just need to take two that we know. I know A and, all right, we're going to use C because we have both of those. So we'll have 105,214.26 over cosine of 70 equals, I'm going to figure out A first. A 300 over sine of A. So that divided by 70 cosine equals that 307,625.9. So that equals that number. Bring sine up over here. Sine A. So 300 divided by that. So store 1. 300 divided by recall. Sorry, guys. 300 divided by recall 1. Inverse sine. Okay. Whoa. I see what's happening here. So A equals 0.00186. So it's a really small angle, which is what I was expecting, you know? So this angle is 0.00186 degrees. All right. So now I know 70. I know that. Now that plus that minus 180 is going to give me this angle. So that plus 70 equals that minus 180. Yeah, I did something wrong here. I have a feeling it's this. Let me see.
It's okay.
But
We're getting out of time.
So
Yeah,
I think
that's-
we're on the right track on this, Dane, is figuring out one of your other angles. And then
Okay.
I revert to field surveyor mode on this. And I just would traverse, I would call this line an east-west line. I would traverse in a southeasterly direction to the distance to this point of the instrument. And then from there, I would do a bearing intersection from point, whatever this is,
Yeah.
to going east, and from the instrument going north to find that. And your distance along this leg is your station difference, and your distance along this leg is your offset.
Okay.
And I know there's a formula to do it, and there's a way to do it in my HP 35, which is still packed somewhere here.
Yeah.
Okay, or I could just reset up here and here and get these two angles, right?
Yeah,
Like
but you
these.
don't want to do that. That's time is money, right?
Yeah,
So-
okay.
Tell you what, let's take a look at this one for next month, and
Okay.
and we'll hit this again hard.
Yeah. Yeah, I really appreciate it. I'm looking at comments now. I don't really see much, but I'll read through and make sure I answer anyone. But if anyone has any questions, please reach out to me. I'm at surveyingmanual@gmail.com. I'll put it up in the chat right away at the beginning of this. So if anyone has any questions, please let me know.
Okay, and there are some links in the chat for those of you that are still on. for different books and websites and workbooks and videos.